All right, hey, it's Jeff. I wanted to give a shout out to one of our people on our team in Kent, Washington. Isaac, man, thanks so much. Last night he ran a call on a conveyor. The symptom was the machine had no power at all. We've been down there a couple times, and we were thinking that last time we'd gone down there, the toggle switch on the conveyor wasn't on. So we hassled him a little bit, and we went down and we checked it out. And sure enough, nothing was working on the machine. When he got there, he was able to activate the contactors by energizing these, and he was able to prove that the motors would come on. So what we established is he set the machine for the meter to voltage, and then he checked for voltage from ground to L1, L2, and L3, and he got 110 volts on each of those legs. What we did next is we checked for voltage on these two wires together at the bottom of the transformer right there, and we got 208 or 213, whatever. And I verified that we had the same amount of voltage with the fuses in place up here. When he went to check the voltage on the downstream side of the transformer, we expect to see about 110 volts. And he checked to see if he had voltage between the white and the black wires, and he had nothing. So we knew that we had power available at the primary coil in the transformer, the 208, and we had nothing coming out. And when we pulled the fuse out, we determined that the fuse didn't have continuity, meaning the fuse was blown. Well, a lot of us have been in this situation, and our best thinking is to turn the power off on the machine and to replace the fuse and kind of hope for the best when we turn on the machine. What we did instead is he had the wherewithal to give me a call, and we started talking through it, and I knew from experience that anything that's downstream of the fuse is going to be the root cause of why a fuse blows. When something downstream draws too much energy, maybe because it's going bad or it's working too hard, then the fuse will burn on purpose so that it doesn't overtask the transformer in this case, or in another machine, cause an issue inside the house or the building. And we established that once this fuse was blown, that we had some sort of a load downstream that was causing it to fry. And the common items that are the loads on the control circuit on the machine, we have two fill valves, one for the wash tank, one for the final rinse. We have all of the magnets that are involved in any of these contactors. So the coil behind each of these contactors requires energy to do its work and magnetize and pull the contactor points down. There's two contactors down in the heater section. We have a coil inside of each of these ice cube relays. That's what this little copper thing is. And then we have a light bulb and some other stuff. And in my experience, the most common failure on the control side of our machine has to do with the fill valves. And each of the solenoid valves are effectively the same as the autochlor solenoid, even though they have a different housing on them. But the guts are the same on the inside. So the magnet is designed to do just enough work to lift the piston up on the valve and open up, and then the water closes itself down. So what I had him do was to snoop around for the wires that go finally to the two valves in the back. And here's what we found. When I take the cover off of the micro switches that are in the back where the fill micro switch is, I can see three wires back there. One is a black wire, one is a blue wire, and on this one there's a yellow wire. And the same thing is on the other end of the machine, except the yellow is now an orange. And in this case, this machine travels a certain direction. This is the wash, and then the exit is on the final rinse on the left hand side. The two valves that we have are going to be one main fill for the wash tank, and then one for the final rinse on this machine down at this end. And on his machine was reversed, so he had the final rinse valve on this end of the machine. The wire back here, the blue wire, is the wire that powers up the fill for the tank on the machine. And that blue wire is teed together with both switches on each end. So here's what we did. We took the meter and we turned it off and we set it to ohms. And then he got it out of the way. I'm going to set it here so we can kind of see the number. But he took one lead, and with the power, again, the power's off. We've got the toggle switch turned to the off position. I take one lead and I touch any white wire. In this case, I'm just going to put it in one of the Phillips screws on the common, what we call the kind of the common bus, or the neutral bus on this machine. Has all the white wires are connected together. And then I'm going to reach over here and I'm just going to touch the metal on the terminal that would go to the blue wire here. And I don't generally even have to take it off. But I'll take a look at the meter now, and the meter is kind of figuring out what it's doing. And I've got a number that says, I just lost connection. I'm going to wait till it's steady. 166, 170 ohms, somewhere in there. That's good enough for me. And then the other valve for the final rinse, the end of that wire is the purple wire that you can find easy inside of the control box right here. And you'll see if you take a look in here, the purple wire ends up connecting to what looks like a quick start. It's a little black timer relay, and this relay is the 6-second delay relay that waits for the final rinse to come on so that it's not pumping water when we don't need it. But the purple wire is attached to this, and the way this works is, here's the main power. When it gets a signal from the final rinse to come on, or from the rinse pump to come on, then it counts to 6, and then it lets power out into the purple wire, which eventually goes to the fill, and that's what turns on the final rinse fill valve. I'm going to do the same thing on this one. I'm going to go ahead and connect a white wire anywhere back here. In this case, I'm just going to use the power switch because it's just as easy. It's another example of a place to grab a white wire. And then I'm going to touch the purple wire with my meter, the other lead. And the display reads 170 ohms or so, just about the same as the other one. Now last night, one of those two coils was 165 and the other one was 12. So just to make sure, what we did is we grabbed another coil out of the truck and we attached one lead to one wire and one lead to the other wire, and I've got 166 ohms. So as a reference, the brand new one gave me a number that was very close to the one that was in the machine that was still good, and I was able to identify with him the one that was bad. So we replaced that coil, we put the fuse back in line, the machine ran great. So a little bit of insight on how I would use ohms to make a diagnosis in the field to make sure that if I replace a part, that it's actually the part that I need to replace. Just for fun, here's a heating element. And if I had a heater that if I had a machine that wasn't heating as much as it normally did, say it's A6 and it goes into its temp check, and all of a sudden after a few months it's been working fine, and then it sits there in the temp check now every cycle, it may be that one of these three heaters isn't doing what it's supposed to. I would be able to easily identify that with a clamp around the wires that go to the heaters, each three wires, and if one was higher than the other two or vice versa, then something's going on. But the real test is to take these wires, and I take my lead on the voltmeter, I touch one lead to the gray wire here, and the other end of that heating loop is the other gray wire. And whatever my reference number is, in this case 16.8, I'm just going to use that number as a basis to compare the other two. I'm going to do the purple, and here I've got what I'm imagining on a new heating element is about the same, and yeah, it's really close, 17. And then I'll do the last one, which is the brown combination. And I don't care so much what the numbers are supposed to be. I'm just looking to make sure that they're about the same as each other. And that one's 16.8. In the case of a heater that wasn't working properly on all 3 coils, meaning one of the heating elements wasn't doing what it was supposed to, the machine would take longer to heat up, and it would show up as a number that was different than 16.8 or 17. Maybe it'd be 2 or maybe even 900. Doesn't really matter to me. They should all be the same, and the one that's the outlier is the bad one. Chemical motors on our pump, the 3 Perry pumps that we have, same thing. I think I remember that the ohms reading that I would get when I checked a chemical pump is about 10-ish. Somewhere between 9.5 and 10.5 is probably fine. If I had a machine that had blown the fuse on the chemical pump fuse, which is one white wire that controls all 3 of them, if that fuse had blown, then I would do the same thing. I would unplug the 3 motors. I would check the ohms on each motor. I got 10, I got 9.9, and I got 900, or I got 0, or I got whatever. That third one, or whichever one it was different, might be the one that needs to get replaced. So I just don't put a fuse in and hope for the best. So good job, Isaac. Good job being patient. Good job reaching out for help when you needed it. And good job having a cool head and staying cool with the customer breathing down your neck. That's amazing. Good job.